I already did a video finding the intersection between two 3D lines. And so this is kind of related to that because we're going to be dealing with parametric equations for 3D lines. But in this case, I want to find the distance, the shortest distance between a point and a line in 3D. Now, there's actually four, count them, look, four, there's four fingers. There's four ways I'm going to do this. It's going to be awesome. So I'm going to do it numerically in Python, and then I'm going to use a derivative to find that distance, and then I'm going to use the dot product, and then I'm going to use cross product. So I'm going to just do all of these. It's going to be like a what was that concert, that big concert? Oh gosh, well, it's a big concert with a bunch of bands in it, and these bunch of bands are math. So here's the problem. I'm going to give the problem, and then I'm going to explain briefly parametric equations for lines. So I have a point RQ, and I found this value somewhere because I wanted it to kind of work out nice, and it kind of does, but it doesn't also either. And so this is the x, y, and z coordinate of the point that I want to find the distance to. And here's a line in parametric form. This is called parametric. And this can be kind of confusing to understand parametric equations because these are my values of a point. X, y, and z are the point on a line. And you can move along that line by changing the value of t. So if I put in t equals 0, that may be right here. And then t is 1 there, is t is 2 there, t is negative 1 is right there. So I can move along, and with a t value, I can find all these points. Now, I'm a physicist, and so I think of these in physics terms. So in physics terms, I like to think of this as a position, 3 coordinates of a position x, y, z. So I could just say r equals x, y, z. And then I can think of t as time. So if that's the case, this is actually like the velocity is the change in r over the change in time, which is going to be equal to r minus r0. The position was at 0 divided by t minus t0. So if I consider t0 to be 0 and r0 to be the position at t equals 0, whatever that value may be, then this is just like velocity. So you could this equation is the same as v equals, I'm sorry, it's not, r equals r0 plus vt, where this is, we think of this in terms of time. And that's the initial position at time t equals 0. And you can't have negative time too. So if that's the case, then I can look at these coordinates in front of the t term and I can get the v, right? Because that's my t, everything in front of that would be my v. So r0 in this case would be this initial value, so that would be negative 2, 1. And v would be equal to 3 in the x direction, negative 2, 4. And so now I can think of it in terms of a point and a vector. So these this is the same as a point vector equation. So I like to think a point and a vector. This is a point on the line, and this is a vector in the direction of the line. And it's the same as this. Okay, so how can we do this distance numerically? Well, what I'm going to do is treat this as just like a ball right here. And it's at some location, r0. And it has some velocity, v, and this is at t equals 0. So if I do that, I can break this into a small time step, let's say delta t equals 0.01, and use that to find out where it's going to be at the next position. I'll call it r1. So r1 would be equal to r0 plus v delta t. So it's important to have that delta t. And then I can find the next position, r2, would be r1 plus v delta t. So I could just always look at the position before it and find the next position based on that delta t. Technically, you could use just t and the initial position every time, but I like to do it this way, and it's my video, so you have to do it the way I like to do it. So now what about the distance? So let's say that here is my line, and here's my ball moving in this direction v along this line at different t's, and then here's my point. What did I call that? Did I have a name for that point? RQ. I don't know why I use Q. And so I can calculate, I know the location of this is called that R. And I can find this vector. Let's call it R, let's call it the vector D. from my point to from the point of my line to the point where I want to find the distance to. And so that would just be d would be vector, would be rq minus r, whichever that point may be. So then the magnitude of that would just be the magnitude of that vector, and that would be my distance. So what I'm going to do is take this, make this line, move a point along here just like it's a ball, and then put that point there, and then just measure the distance. I measure the distance and plot distance as a function of t, and from that we should be able to find the shortest, so that we're looking for the shortest distance, so it'd be when those are perpendicular. We'll use that later. Okay, let's jump over to Python, because I think it really helps to visualize this whole thing in Python, and I actually got a head start here, just a little bit of a head start. I apologize, but I was just excited. Okay, so here I have what was given. So there's my point on the side of the line, and then there's my parametric equations as a line, and I wrote it as a comment. Is that the same equation? Yeah, okay. R0 is not -2. Look, I made a mistake. R0 is 0, right? Because it's 0 minus 2t. So this is actually 0. Sorry about that. I'm glad I caught it, though, because that would have been embarrassing. Okay, so I have my point, which is where I'm starting. That's my, no, I need my point, so I need R0. So let's say, let's just write that out. So let's say R0 is equal to the vector, and it's going to be the constant term in each one of those. So it's going to be -2, 0, 1. And then I need my velocity vector. I'm going to say v is also a vector. And I'll point out something in a second. And it is 3, -2, 4. So I'm using GlowScript VPython here. I didn't say that. And so GlowScript VPython has all this really nice stuff about it. It includes vector handling. It includes three-dimensional objects, which I'm going to show you in just a second. And it runs in a web page, so you don't have to install anything. Now, I love it. So there's actually glowscript.org. I'm using trinket.io, which has GlowScript in it, just because it's easier to share the code. You can see the code, and you don't even have to log in. Okay, so let me just show you this. Print v. So it does indeed treat that as a vector. So there's my vector value. And so you can add vectors together and take the magnitudes and the unit vectors and cross products and dot products and all this stuff. The other nice thing is I can make an object like this, sphere. And it makes a three-dimensional sphere. And I can actually rotate that around. It's got lighting. I can change the lighting. I can zoom in and out and all that stuff. Okay, so let's make the ball. Let's make a ball. I should call it R. No, let's just make it a ball equals a sphere. I'm going to put it at the initial position. So I'm going to say position equals R0. And I'm also going to give it a radius. So let's say radius is equal to 0.1. And let's give it a color. Let's make this window look bigger. Let's give it a color. Color equals color.yellow. And let's turn on this. Make trail equals true. So that means when the ball moves, it'll leave a trail behind. So if I do this now, it'll look a little bit different. You can see there's my ball over there because it started at -2, and this is actually in 3 dimensions too. So, but it started off to the side. Okay, so now let's go ahead and move it. So I'm going to say t equals 0, dt equals 0.01. That's the size of my time step. That's how far it's going to move each time I draw the ball. Now I can say while t is less than 3, I'm going to put this rate 100. So rate is a statement in GlowScript VPython that tells it how fast to do the animation. So this would do no more than 100 calculations a second. So it would take 3 seconds to run this if the time step is 0.01. Now I'm going to update the position of the ball. Ball.pos is R, right? Because that's the location. And it's going to take that, add it to the old value, plus v times dt, and then I'm going to update time. And let's run this. So there's my ball, and it's leaving behind a trail, and the trail is the line. So that's my 3D line right there. And you can rotate this around and see it in different viewpoints also. Okay, let's make my RQ point. So let's say ball, let's just call it RQ. Yeah, let's call it RQ. And it's a sphere. Its position is the vector. Oh, I can't do RQ because I have RQ up there. So let's say Q ball. That's going to get me in trouble because I have trouble typing cue. But cue ball is a sphere. The position is RQ. The radius is also 0.01. And that's just how the size it looks. And then let's make this the color equals color dot cyan. Just so we can see where that ball is. And I don't even see it. There it is. Okay. So you can see that it's kind of hard to rotate this around 3D, but over here, that's when it's at its closest approach. We want to find that value. So what I'm going to do now is I'm actually going to use another 3D object called the arrow. I'm actually going to draw an arrow from the ball to the point. So let's call this D arrow. D arrow is a type of object, arrow. It's already built in. And arrow has two important properties, the position. So I can say the position is equal to ball.pos. And the axis is a vector from the position to the end. So this is going to be equal to, axis is going to be equal to qball.pos minus ball.pos. Right? So I'm going to draw that vector from one to the other. And let's just leave it as white, and that's fine. Now down here, I'm going to need, as the ball moves, I need to move the arrow and change the arrow. So I need to change the position of the arrow. darrow.pos equals darrow dot, no, it equals ball.pos. That means it stays attached to the ball. And then there's another way to do that, but this is the old way. And then I need to change the axis. So darrow.axis is equal to qball.pos minus ball.pos. So I'm doing that again, right? Because those values changed. So I need to recalculate that. And let's see what it looks like. And so the arrow is actually really big because it keeps the same proportionality. But you can see how that would look. And I think that's kind of nice. Okay, let's make a graph. Let's plot a graph of that distance. I'm actually already calculating that distance right down here. So let's just put it up here at the top. I'm going to say G1 equals graph. Title equals distance to point. And let's give it an X title of just T, the parameter T, which is time, right? But we don't have to do it that way. Y title is equal to distance. And let's put this width equals 500, height equals 250. That would just make it a little bit bigger, smaller so we can see it better. And that just makes the graph. Now to plot something, I need something to put on there. I'm going to use G-curve is a series of points. So Python will put a point and then connect them all by line. So it'll look like a curve. And I'm going to give this a color, color.blue. Okay, so down here, let's actually calculate the vector D. So D equals qball.pos minus ball.pos. So that's going to be the vector from the line to the point. Now I can plot. I can say f1.plot and plot a point. I want my t value on my horizontal axis and the magnitude of that vector D on the vertical axis. So magnitude is a built-in function in Python, so I can just say mag d, and then it'll do that. So let's just see what we get. And pull this over. And there you can see our answers, right? It starts off far, and it gets closer and closer until it gets to the closest point. And then at this closest point right here, my t value looks like it's right around 1, and in fact is 1. And so I know the t value. So let's go ahead and calculate, and the distance I can get also. See, there's a distance on this axis right there. It's right at 2.44 from this, it looks like. So let's go ahead and plot that ball. So if I say TD equals 1, that's the time of the closest approach. Now let's put, should we call this? RP. RP equals sphere. Position equals, I guess I should calculate that. But let's go ahead and say R0, let's put it as a vector of parentheses, R0 plus V times TD, right? Because that's my T parameter. So I can do all of that right in there. And let's put the radius a little bit bigger. Radius equals 0.15 so we can see it. And what color? Let's make it red. Okay. And now let's run that. And it'll put it in. I'm going to get rid of the. I can get rid of this arrow. It's just distracting me. now we'll run it. Okay, there's my point right there. And that's the closest approach. So we could actually change this down to something like 1.5, and we could even draw a line. Let's draw a line. So I'm going to let's make it a cylinder. LP equals cylinder. POS equals RP.POS. Axis is equal to, I think it's just D, right? It should just be D. No, that's the oldest D. Okay, so it would be our QBall.POS minus RP.POS. And then the radius, let's put the radius at 0.1 and make it red. Okay. Oh, something happened. Too many parentheses. Oops, let's see. And I'm going to give you this code. I'm making things hard for myself. Red. Why is there too many parentheses? Oh, let's see. That's not what I wanted. I think I have too many right parentheses. I think I don't have enough left. So there's cylinder, POS, axis, aha, right there. That's where I need one. Okay, there's my distance. I think that looks pretty cool, right? And it is right. It is a right angle. You can see that it is right angle. Okay, and I have that. I guess I should print that value too. One more thing, and then we'll move on to the next method. Okay, so down here, let's just say print D equals. I told you I'd do it numerically, so I have to do it numerically. And this would be magnitude of QBall.POS minus RP.POS. Now, it's possible if you did not see a minimum on that curve, right here, if there was not a minimum, you just have to change the values over which you plot, you run t. I mean, maybe t is -5 to -3. I don't know. You'd have to see. Okay, so, but there should be a minimum somewhere. And it is possible that it could be 0, because that would just be the line passing through the point. That's possible. But there will be a minimum distance, and you can find it that way. So I have 2.4494. Let's go and do another method, because we can see here another method. If I can get distance as a function of time, I can find this minimum by taking the derivative and setting it equal to 0. So now it's a max-min problem. Okay, so let's switch back over here to the paper and do this as a max-min problem. Okay, so I need, let's just write this. Here is my generic line. And then here's a point on that line. And so the value of that point, I'll call it, I was just calling it R. R is going to be X, Y, Z. But I know the values of X, Y, and Z in terms of T right here. So I could say R is going to be equal to the vector -2 plus 3t minus 2t, 1 plus 4t. And then my point, they write that down, RQ is equal to 3 minus 1, 4. So let's get, and so here's my point, and I'm going to find this vector D and take the magnitude of it. Really, I'm just finding the distance between these 2 points. So I can just use the Pythagorean theorem and say D is equal to the square root of this minus that squared. So I'm going to say 3 minus 2 minus 3t squared, right? Because I have to, 3 minus, let's be plus. 3 minus this, yeah. Plus -1 minus -2, so plus 2t squared, plus 4 minus 1 minus 4t squared. Okay, so let's just make this a little bit simpler. So I have 3 plus 2 is 5 minus 3t squared plus negative 1 plus 2t squared plus, this is going to be 4 minus 1 is 3. 3 minus 4t squared. Now let's square all these things. So I get 25, and then I get plus 9t squared. Now the cross term is going to be 5 times negative 3 is negative 15. I get that twice, so I get negative 30t. I feel like I've gone off the deep end with the small error. I did work this out beforehand, so I'm going to double check. No, it looks like I'm okay. Now right here, I'm going to get negative 1 times negative 1 is 1, and then I get 4t squared, and then I get negative 2t twice, so it's going to be negative 4t. Here I get plus 9, and then I'm going to get 4 times plus 16t squared. And then I get the cross term of negative 12 twice, so it's negative 24t. Okay, so let's combine our like terms. So I have 9t squared plus 4t squared is 13t squared plus 16t squared is 29t squared. Yeah, 29t squared. Now my t terms, I have negative 30, negative 34, negative 34, negative 58. Yeah, negative 58t. And then I get 25, 26, 35. That's it. And I'm going to write this as 29t squared minus 58t plus 35 to the 1/2 power. And that's d. Now I want to take the derivative of d with respect to t, which seems kind of weird. So let's just put that right here. So the derivative of d with respect to t. I want to take the derivative that gives me the slope. I want to set that slope equal to 0. So this is going to be bring the 1/2 power down front. So I get 1/2 and then multiply by all that stuff. 29t squared minus 58t plus 35 to the negative 1/2. Now I have to take the derivative of the stuff inside. So I get 2 times 29 is 58t minus 58 and then 0. And I'm going to set this equal to 0 to find the value of t. Now it's kind of complicated, but here's a term right here, and here's a term. If either of those terms is 0, then the thing is 0. So I'm going to set this one equal to 0. So I'm going to say 58t minus 58 equals 0, so t equals 1. And hint, that's what we had before, right? That's what I got from the graph, so it agrees. Now I can go back in my distance formula. I could do it any way. I could use this formula up here. And I could say distance is equal to 29 times 1 squared minus 58 times 1 plus 35 to the 1/2 power. And so this is, let's put it in the calculator. I'll make a mistake. I could probably do that. It's taking the square root. It's not going to be easy. So I'm going to say square root. I'm not good with calculators, I'll be honest with you. Square root. Where's the square root? There's square. There it is. Square root of 29 minus 58 plus 35, close parentheses, enter. 2.449. Same thing. Okay, that was method. So we've now done it 2 ways. We've done this, check. We've done this, check. Now the dot product. So let me draw a picture, and then I might draw this in Python. Let me get some more paper. So here is my line. And here is my point. And then here is a parametric point on my line. So if I have this is my vector v, the direction of the line, and let's call this the vector u, or I call that d, the vector d. I'm going to get the shortest distance when this is true, and that's a right angle, right? So if two vectors have a right angle between them, then I could say, so I say if theta equals pi over 2, then v dot d equals 0. So let's just get an expression for d. I already have a value for v. Take the dot product and set it equal to 0. And that will tell us where t is, right? Because remember, these are different t values. Okay, so I can use any point. It doesn't matter. So I'm using a generic point. So I'm going to go back to using my same generic point, which was, I'm looking for my parametric equation. No, that's not it. I got too many sheets of paper here. Right here. Okay, so here's my point. I'm going to write down my velocity, v, equals, you think I'd remember this, 3, negative 2. I don't need that. Well, yeah, I do need that. 4. And then my point, let's just call that r, is going to be equal to negative 2 plus 3t minus 2t, 1 plus 4t. So I need that so I can find this d vector, right? So d vector would be this point rq minus r. And so rq, gosh, you'd think I'd remember this. You really would. But no. 3, negative 1, 4. So now I can take the difference between RQ and that generic point right there, and I get the d vector is going to be equal to 3 minus negative 2, so plus 2, minus 3t, and then I'm going to have, I did this already, negative 1 minus that, so negative 1 plus 2t, and then 4 minus 1 minus 4t. And let's just simplify this, so I get 5 minus 3t minus 1 plus 2t, and then 3 minus 4t. That's my vector d for some arbitrary point, right? So it could be anywhere along there because I could have any value of t. Now let's say v dot d. So if you remember, if I have two vectors, a equals ax, ay, az, and b equals bx, by, bz, then a dot b is just a sum of the product of their components. So this would be ax, bx plus ay, by plus az, bz. So in this case, I just need to multiply the components together and add them all up. So this is going to be, I'm multiplying my v, this. So it's going to be this times this. So I get, let's just do it all in one step, 15 minus 9t plus, now I'm going to take negative 2 times this. So I get 2 minus 4t. And then I'm going to get 4 times this. So it's going to be plus 12 minus 16t. And I want to set that equal to 0 because also the dot product is a dot b equals the magnitude of a times the magnitude of b times the cosine of the angle between them. So if the angle between them is pi over 2, the dot product is 0. Okay, so let's just combine like terms. I have negative 9, negative 4 is negative 13, so I have negative 29t, and then I have 15, 17 plus 12 is 29 equals 0. And here you can see again, t equals 1. So this agrees with the other two ways that we've done it. They all agree. Okay. And you can say, oh, this is dumb because it's too much work. Fine. I'm not doing this because it's too much work or too little work. I'm doing it because it's fun. Okay. Just letting you know where I stand, so you don't have anything, some false assumptions about what's going on here. This is fun. So now once I know that t is equal to 1, I can just plug in t equals 1 into this vector and find the magnitude of it. And so let's say, I'll do another piece of paper. So the magnitude of d is equal to the square root of this component squared, and on t is 1, so I'm going to put 3 plus 2 minus 3 squared plus this component squared, which is going to be negative 1 plus 2 squared, plus this term squared, which is, why did I do it that way? Oh, okay, whatever. Which is going to be 3 minus 4 squared. So it's just a number. So it's going to be 5 minus 2. The square root of 5 minus 2 is 5 minus 3 is 2. 2 squared is 4. This is going to be 1 squared. And this is going to be negative 1 squared. So I have the square root of 6. Let's just see if it's the same thing. If I made a mistake, I'm just going to blame something. I don't know. Square root 6. Oh, I get a different answer. I must have made a mistake somewhere. Okay, let's see. Let's just check it again. Let's use this. So it's going to be the square root of 5 minus 3, so 2 squared, 4, plus 1 squared, 1, and this is 1. Square root of 6. Well, I got the t value of 1. So let's put t in up here. Let's say r equals negative, this is going to be, t is 1, so I get negative 1. I get 1, negative 2, 5. And then rq is, there it is, 3, negative 1, 4. Okay, so now let's just take, I'm going to do this in one fell swoop on the calculator. So I'm going to say square root. So it's going to be this minus this squared. So that's 4, right? Yeah, 4. This negative 2 minus negative 1 is, I'm going to get the square root of 6. Well, that's not the same thing. Okay, well, I'm gonna leave this as a homework. I'm pretty sure I did the t right. I don't know what's going wrong. I'm making some dumb mistake. I'm positive. Actually, let me just double check right here. 2, 3, negative 2, 1, 4t, 3. Okay, let's just do the last method because I want to. And that's going to be the cross product. I mean, I already have a 33-minute video, right? Is there a time limit on YouTube? I know there's not. I was joking. Okay, so now let's think about this. So here's my line, and here's a point on the line, and here's my point that I want to find. And I want to find this distance. So I can draw this vector d like that. And that's the vector d. And I can find the magnitude of that. And then imagine that this is some angle theta, and this is the direction of v. So here I have a right triangle. And so I could find the length over here as, I could say sine of theta is equal to the opposite, which is going to be d min. Let's call this d min, dm for the minimum. D min divided by the magnitude of this, which is d. And that's just some arbitrary point. That's not necessarily the distance. So then I could say d min equals d sine theta. Okay, that's pretty cool. That's just a scalar value, right? Now I can go to the cross product. If I have two vectors, A same ones, ax, ay, az, b, bx, by, bz. Then I can find the cross product two ways. I can say A cross X is the resultant of the following determinant, X hat, Y hat, Z hat, and this will be AX, AY, AZ, BX, BY, BZ. And so this gives me the vector, it's going to be kind of messy. X hat's going to be AY, BZ minus AZ, BY. The y component is going to be, there's a negative sign in the y component because it's the 1 term. So that's going to be bx az minus ax bz. And then the z component is going to be ax by minus bx, that's a y, ay. But if I find the magnitude of that, I can get something else. I can say the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And you see here I have the magnitude of D and the sine of theta. So if I do the following, let's say V cross D, the magnitude of that is going to be equal to the magnitude of V times the magnitude of D times the sine of the angle between them. And so if I get D sine theta, that's what I want. So if I divide this by the magnitude of V and divide that by the magnitude of V, then I have the magnitude of D sine theta, which is dm. So it's kind of a little trick, but if it works, it works. Okay, so let's just, I'd only need any point on this. It doesn't matter what point that is, right? Any point. And I need the velocity, the vector for the line. So let's do this. So let's just use the point r0. So I have d equals, let's see, r0 is the vector, and goodness gracious, I forgot this already. r0, that's RQ. RQ is 3, -1, 4. R0 is, oh, that's not my first page. R0 is -2, 0, 1. Okay. So, and then my velocity, V, you'd think I would memorize this by now. 3, -2, 4. Okay. So D is going to be the vector from this point to that point. So D is going to be equal to the vector 3 minus -2, so 5. -1 minus 0 is -1. 4 minus negative, what the heck? That's just 1. 4 minus 1 is going to be 3. That's my vector D. There's my vector V. So now I need to find the magnet. I need to do D min is going to be equal to V cross D divided by the magnitude of V. Now, I'm going to actually do this in Python because I have V, I have D, and the cross products isn't that much fun. So I want to show you how powerful Python is because we can do this in Python. So let's switch over here to the computer view. Oh, 39 minutes. All right. Okay. So I have the vector V. I already have that. So let's say D min equals the magnitude. I need the vector D. So let's say D, let's call it D0. D0 is equal to RQ minus R0. Right? So that's just from that 0 point. But it can be any point. It doesn't really matter where that is. So now I need to take the cross product of V and D. So I'm going to say cross. It's a built-in function in Python. Let me get a little space up here. Cross V, comma D, 0. That's the cross product. Now I need to divide that by the magnitude of V. Oh, and I took the magnitude. Divide by the magnitude of V. And that should be it. So let's say print D equals D min. Hopefully this works. I was going to run first. Boom. Boom, it did it. Okay. So yeah, the cross product method is the easiest way to do this. But I think if you really want to think about what's going on, those other methods really help you visualize what's going on. I mean, if you just come in and say, oh, the distance between a point and a line, V cross D divided by the magnitude of V, it's like, it just doesn't really make sense. I mean, why does that work? I mean, it does work. It gives the same answer. I did mess up on that dot product one. I'm going to think about that, but I'm going to let you think about that for homework. But those are the 4 ways that you can find the distance between a point and a line for fun.